Realize that cotton is naturally a deep-rooted plant because subsoil conditions in the southeastern United States are seldom favorable for development of a deep-root system. So crops in this region usually are not able to make most effective use of water and nutrients stored in the subsoil. In the following scenes, we will show some of the physical and chemical soil conditions that can restrict cotton root growth. Soil compaction is a major problem in the southeastern United States. The cotton on the left was grown on a compacted subsoil. The cotton on the right was grown where the compacted subsoil was loosened by chiseling. When we look at the root system from the compacted area, we can understand the difference in top growth. Notice the small taproot and the sparse horizontal lateral roots. A cone penetrometer is a useful instrument to study soil compaction in the field. With this penetrometer, you can determine depth and strength of the compacted layer. The subsoil was too strong for the penetrometer to be pushed through. Next, a trench was dug across the rows of cotton grown on the compacted subsoil. There was considerable root growth in the surface soil, but none of the roots had grown through this strong compacted layer. Even though the cotton was wilted, soil at the 2-foot depth was moist. When a trench was dug across the chiseled rows, cotton roots had penetrated at least 30 inches deep. This vigorous root system could withdraw water from a large soil volume. The cotton was not wilted except at the edge of the trench. To study more closely the effects of soil compaction on root growth, we built a soil box with a glass front. A severely compacted subsoil was placed in the left compartment, a moderately severe one in the center compartment, and the right side was filled with loose soil. The moist surface soil was loose in all 3 compartments. One movie frame was taken every 3 minutes. First, notice the cotton roots in the left compartment. The roots have now struck the compacted layer and have started growing horizontally. Next, look at the center compartment. The roots have penetrated the compacted layer about a ½ inch and have now apparently stopped. In the loose soil on the right-hand side, the roots have continued to grow vertically. Lateral root development has started in all 3 compartments. We have a close-up view of root tips as they strike a compacted layer. Notice the root in the center as it buckles. Now watch the root thicken just above the compacted layer. Downward growth of all 3 roots stopped soon after they struck the layer. Two days later, the tap roots have died and laterals have developed on top of the compacted layer. The wet, puddled soil on the left contains low amounts of oxygen. The wet, loose soil on the right side has adequate aeration. Notice that roots growing in the puddled soil have almost stopped, except for the one root that has found a soil crack. These cracks provide paths through soil layers that would otherwise stop root growth. Here we show the effects of 3 levels of subsoil water on root growth. In all 3 compartments, surface soil was at field capacity. In the left compartment, the subsoil was at field capacity. In the center one, the subsoil was moderately dry. In the right one, the subsoil was at the wilting point. Notice the difference in color caused by the soil water content. In all three compartments, roots entered the subsoil, but the rate of root growth soon slowed in the two drier soils. By now, you can see the difference in root length. Observe that lateral roots have developed in the surface soil of the two drier compartments. By now, lateral roots have begun to develop in the left compartment where all of the soil is at field capacity. One of the common problems in root development is that of unfavorable soil temperature in early spring. Here we illustrate effects of a cold spell on root growth. All three compartments were planted when soil temperature was 80 degrees Fahrenheit. When you see the signs, temperature of the center compartment was lowered to 60 degrees and that of the left one to 70 degrees. Root growth immediately slowed to 1/12 inch per day at 60 degrees and to 1 inch per day at 70 degrees. At 80 degrees, root growth continued at 2 1/2 inches per day. The cold temperatures also slowed the rate of emergency. Notice that the seedlings have now emerged at 80 degrees Fahrenheit and now at 70 degrees. At 60 degrees, growth was much slower, but the plants finally did emerge. Subsoil acidity is a prevalent chemical condition in the southeast, and it can cause shallow rooting. These plants are growing in a plot where the subsoil is only slightly acid. Many roots were found in the subsoil extending to a depth of more than 2.5 feet. Subsoil pH was about 6. Where the subsoil was very acid, about 4.5, there were few roots below the plowed layer. Top growth on strongly acid subsoils was much less than where the subsoil was only moderately acid, and yields of lint were sharply reduced. These plants show the difference in taproot development and top growth caused by subsoil acidity. Plants with severely restricted roots usually wilted within 3 or 4 days following a rain, while those with deep roots seldom showed signs of wilting, even during periods of up to 2 weeks without rain. We grew cotton seedlings in subsoil from the field plots placed in glass boxes and measured the effect of degree of acidity on rate of root penetration in the subsoil. The surface soil in all three compartments was limed to a pH of 6.4, but the subsoils ranged from pH of 5.2 in the center cell to 5.5 on the right and 6.5 on the left. Root growth into the very acid subsoil has practically stopped, and that at medium acidity has slowed down considerably. Roots continue to grow in the well-limed subsoil. Cotton root tips damaged by acid soil usually seem swollen, and the tips have a twisted appearance. Normal roots, undamaged by soil acidity, are thin, white, and grow straight in loose soil. Available calcium must be present in all parts of the root zone for root growth to take place. It cannot be absorbed by roots in the surface soil and translocated to support new root growth in the subsoil. Deficiency of calcium for root growth can easily be caused in acid soils already low in this element by application of high analysis non-calcic fertilizer. Here a well-limed surface soil was placed in the 3 compartments above an acid subsoil. The center compartment was lined with magnesium carbonate, and a conventional rate of a 14-14-14 fertilizer was applied. The other compartments were lined with calcium carbonate, and the one on the left also received the fertilizer application. Root growth in the center compartment was stopped completely by a lack of calcium soon after the tips entered the subsoil. Fertilizer placed beneath the seed or too close to the line of initial root growth can cause damage to seedling roots. In this test, an amount of 8-8-8 fertilizer, equivalent to a field application of 800 pounds per acre, was placed in a band in the left compartment. The same amount of fertilizer was mixed with the surface soil in the compartment on the right. Roots growing directly down toward the band stop before they actually reach the fertilizer, showing that the salts have diffused out some distance from their original position in this short time. Growth of the root to the left of the band is also stopped in the same way. Decomposing plant residues, barnyard manure, or green manure crops can cause serious damage to roots of crops planted too soon after incorporation of the organic material. This is especially true for materials having a high nitrogen content, as illustrated by the green alfalfa placed in the soil at the left. The compartment at the right contains no plant residue. Both are filled with fertile surface soil limed to a pH of 5.7. As the nitrogenous organic matter decomposes, some ammonia appears and the soil pH is raised. While this is a temporary condition, the extreme toxicity of unionized ammonia can result in serious damage or death of roots and seedlings within several inches of clumps of organic materials during the period of decomposition. This is the same cotton field shown in the opening scene. It made over 2 bales of lint per acre, reflecting the combined effects of many factors influencing plant growth. Before present cotton yields in the southeast can be increased very much, moisture stored in the subsoil must be used more effectively by the crop. This means that management practices must be developed that will ensure formation of a deep, vigorous root system.